Hi there. So, lesson 7 on transformations. I'm talking about here combining transformations. So, in previous lessons we've learned the following rules, and that is, given the equation y equals f of x, if we replace x with x minus h, or y with y minus k, these result respectively in horizontal and vertical translations. If we replace x with negative x, that is a reflection in the y-axis, and if we replace y with negative y, that results in a reflection in the x-axis. And replacing x with bx, that's going to be a stretch, a horizontal stretch, affecting the obviously along the x-axis. Or if we replace y with a multiplier here, that also results in a stretch, a vertical stretch. In this lesson we're going to find out what happens when we combine different types of transformations. So looking at investigation 1, we're going to combine horizontal stretch and a vertical stretch. So the graph of y equals fx is shown. That's this small semicircle here with the thin line, and it's saying sketch an image of the function after a horizontal stretch by a factor of 3 about the y-axis. So if it's horizontal by 3, this is at 2, it now goes to negative 6, from negative 2 to negative 6, and from 2 to positive 6. This is now followed by a vertical stretch by a factor of 2 about the x-axis. So vertical stretch, heights are affected, so 2, if it's by a factor of 2, anything at height of 2 goes to a height of 4, and so on. Height of 1, we're looking at this dotted line now because we've made this horizontal stretch. So 2 goes to 4, a height of 1 goes to a height of 2, and so on. So we get the thick line as the final outcome of both that horizontal followed by a vertical stretch. Let's do it the other way around. Let's instead of the horizontal stretch first, let's do the vertical stretch first. So a vertical stretch of this, everything will go up by a factor of 2, because that's what we're doing, factor of 2. And as you can see, a height of 2 will go up to 4, a height of 0 basically stays at 0, height of 0 stays at 0, a height of 1 goes to 2, so we get this dotted line again, a different one this time. And now we will do the horizontal stretch by a factor of 3 about the y-axis. Horizontal stretch means this dotted line now goes, if it's sitting at negative 2, it will go to negative 6, 2 will go to positive 6. Sitting on the y-axis doesn't go anywhere. Sitting at, say, I think roughly, what's that, 1? Negative 1 goes to negative 2, positive 1 goes to positive 2, and so on. Here it's sitting at, looks like about, this isn't a very good representation, but you can see what's happening. Stretching by a factor of 3, sorry. So at probably 1, it goes out to 3. And if it's sitting at about 1.5, where would that be? About here, it would go out to about 4.5, so on. So notice what happens in both these. Does the order in which the two stretches are performed make any difference to the final graph? And the answer is no. A horizontal followed by a vertical, or a vertical followed by a horizontal stretch does not seem to make any difference. So we'll get to some general rules regarding order once we've gone through these investigations. Here we're looking at combining a vertical translation and a horizontal stretch. So sketch the image of the function after a vertical translation 3 units up. So we go from here, semicircle, all the way up to this dotted semicircle. That's a vertical translation. Now we're going to have that followed by a horizontal stretch. So what would that look like? Horizontal stretch by a factor of 2 about the y-axis. Sitting at -2 goes to -4, sitting at 2 goes to 4, sitting at x coordinate of 0 doesn't move, and so on. So here's your stretch. So this is the final product. Now let's switch those around. Instead of a vertical translation, horizontal stretch, let's do a horizontal stretch first, and then the vertical translation. So horizontal stretch was by a factor of 2, and then translation was 3 units up. So horizontal stretch, beginning here, we'll stretch it horizontally, as you can see, outwards, to get the dotted line, and then move 3 units up, we get to here. So it looks like in these two diagrams, both these are the same thing. So again, doesn't matter what order you have a vertical translation with a horizontal stretch. Okay, does not make any difference. Now let's look at a vertical translation and a vertical stretch. So we've got the original graph here again, and we're going to do a translation 2 units down, so we get the dotted line. Next we're going to do a vertical stretch by a factor of 3. So vertical stretch of this means if it's a factor of 3 about the x-axis. Okay, so here's the x-axis right here, and we're going to do a vertical stretch. So vertical means if you're at a height of -2, you go to a height of -6. So this point here ends up down here. Same here, at -2 ends up at -6. And so on. -1, it's a factor of 3. This point here goes down to -3, -1 goes down to -3, and so on. So you get this new graph, and anything here on the x-axis will not get stretched. Let's switch these around, see if the order makes a difference. So that was a vertical translation, then the vertical stretch. So let's do the vertical stretch first. Vertical stretch was by a factor of 3. So starting with a thin line, vertical stretch will pull this all the way up to here. So height of 2 goes to a height of 6, and height of 1 goes to a height of 3, and so on. So you get this dotted line with the vertical stretch. And now followed by a vertical translation 2 units down. All of this is moved down by 2, and you can see that what we get is this curve here. Now if we look here and here, it looks the same. It's not actually the same. Notice where the vertex is at 0, 0. Whereas the vertex of this one ends up at actually 0, 4. So we don't actually get the same graph when we change the order here. So yes, it does matter which order things are performed in this particular case. Investigation 4 looks at combining horizontal translation, horizontal stretch. Now again, if you look what happens here, you'll see that the final image, the thick line, is different. It's in different locations in both A and B, in both scenarios. So this was a horizontal translation, 1 unit right, horizontal stretch, factor of 2, and this was switched around here, and so we find there is a difference here. So looking at order of transformations, there is some cases where it does matter. So in general, the order does not matter when 2 translations are combined. So things like going this way followed by this way, or whatever way it might be. 2 stretches are combined. So it doesn't matter if you're stretching up, stretching sideways, such as this. It doesn't seem to matter. Translation and then a stretch, as long as they are at right angles to one another. So translation means we go one way, and then we do a stretch at 90 degrees. Then as long as they're at 90, these two things are at 90 degrees, it will not matter which order we're doing it in. Reflections and stretches are combined. Again, reflections and stretches generally, this is in general, do not matter what order. Now what does matter is when it's a translation and a stretch in the same direction. So you're going to have to memorize that, well, at least remember it. Or if you're combining most reflections and a translation. So what's common here is if it's a translation. If a translation is involved, think twice, does order matter? Because a translation with a stretch or a translation with a reflection, quite possibly the order does matter. Definitely a translation with a stretch if it's in the same direction. That's when a translation and a stretch order will matter, if you're doing them in the same direction. If it's at 90 degrees at right angles to one another, it won't matter. Again, a translation with a reflection, that also order does matter. Now, this is a very important point here. Unless otherwise indicated, use the following order to describe how to transform from one graph to another. Describing the changes. Describe stretches first. So describe any stretches that may have happened first. Describe any reflections that have happened second. And lastly, finish with any translations. So, some kind of mnemonic with S, R, and T, SRT. What would we call, apart from memorizing stretches, reflections, translations? Can we make one up? Maybe make one up for yourself to help you remember that. Class example 1. Describe a series of transformations required to transform graph A to graph B. Okay, so what did we say? It was stretches, reflections, translations. SRT. That's not even an alphabetical order, so you're going to have to remember that somehow. Well, let's look at any stretches. These look pretty much the same shape, so stretches are probably not happening. Reflections, yeah, it looks like there's a reflection taking place. We could have reflected perhaps in the y-axis. So what does that mean? All the x's are becoming negative, for example. And then this looks like it's been moved up to here. This vertex, once it's reflected, would have been moved up to here. So looks like a translation 3 units up, because this graph would have been here if it's been reflected. So it's now here, 3 units up and 2 units to the left. So they say 2 units left, 3 units up. It doesn't really matter what order that's in. Reflection with a translation. In this case, got a reflection, then a translation, or a translation, then a reflection, because these are at 90 degrees to each other. Let's just check what that means again for order matters. Well, above as you read, you can see that most reflections with translations, the order does matter. In this case, I showed that a reflection in the y-axis would end up, coming here. They're doing that, but they mention the translation 2 units left first. It doesn't really matter in this case which way you do the translations, but it does matter probably the fact that you're doing the reflection first. SRT. If I had done the translation first, I think we would have ended up, say, here. Let's clear this first. I would have ended up, say, up here. Then I would have to reflect, and I would get here, and then I would do translation. So I guess you could do it. This looks like you can do this particular reflection and translation in different orders. but be careful. Sometimes it does not work. Okay, moving on to example 2. Describe a series of transformations required to transform graph A to graph B. Here's graph A. Look at graph B. Looks like it's been stretched in some manner. We can stretch about the x-axis, and I think if you get stretched about the x-axis here, this would get higher and this part would get lower, so it looks like that's involved perhaps in making C, I don't know. But to get B, I think we need to stretch this to the right and the left horizontally by, looks like a factor of 2 to make it double the size. So, SRT stretches first, horizontal stretch. So horizontal stretch first by a factor of 2, and then that would bring us out to about here. Let's see if I can draw this properly. There we go. And it looks like this is the center. Has to be brought down by 5, 6, 7 units. 7 units down and 4 units over to get the center to where it should be. So the translations, once you're starting to do the translations, the order of the translation itself does not matter. 4 units left, 7 units down, or 7 units down, 4 units left. How about graph A to C? How do we get A to C? Well, I think that's where we stretch. Oops, sorry about that. Just one sec. I want to just change color of my pen. So, if we are stretching to make C, I think we have to stretch vertically and by a factor of 2. And look what's happened to the center. Starts here, ends up here. So once we've done the stretch, which is the first thing we need to do, vertical stretch by a factor of 2, then we can do the translations in either order. We can move left by 6 and up by 4. Left by 6, up by 4. Notice you can go up by 4 and left by 6. That order in particular doesn't matter. So, looking at part C, graph B going to C, it's sort of being flipped somehow, a 90-degree flip. And I think we can achieve that by doing an inverse function reflecting the y equals x line. Now the y equals x line, if you look at where that goes, it comes through, right through here, all the way through like this. If we do that reflection, this point here will end up across here. This point here ends up here. This point here should end up, I think, 3, 4, 5, 6, 7, somewhere here. And this point will end up over here. So a reflection in y equals, and I guess SRT, I have to keep reminding myself, reflections, we don't need a stretch here. So reflection would be the first thing to do of this box getting us to this point here. And then we have to move it. I'd take the center. Actually, you can take a vertex and move the vertex, or the center. If I took the vertex, it looks like we have to go right by 1 and up by 8. So reflection, y equals x, followed by translation, 8 units left. Oh, they have 8 units left and 1 down. They actually mention other answers are possible. Now I think I looked over this the other day and said 8 units left does not make any sense, because if we're here, 8 units left would take us way over here and 1 unit down. So in fact this is a wrong answer. I think they meant to go 8 units, yeah, I think it's 8 units. This should be up. So 8 units up, and yeah, 1 unit should be 1 unit. 8 units up, that's right, and 1 unit to the right. But other answers are possible. So again, we could go 1 unit right and 8 units up. Okay? Well, class example 3 says describe which transformations are applied to a graph of a function when the following changes are made to its equation. So let's look at the changes to the equation. You're replacing x with 3x and y with y plus 4. Now, if you change the multiplier from 1 to 3, that is going to be a horizontal stretch factor of a third. If you change y to y plus 4, this is moving right or left, up or down. Well, y is the up and down. So if it's y plus 4, if you were to move that to the other side of the equation, it becomes negative 4. So I always like to think of it like that. So this really means 4 units down. And looking at the replacements, starting with this equation here, you see that x has been changed to 3x, y has been changed to y plus 4. Solving for y, you bring the 4 over and you get this equation. We can also, let's see, we can do it in a different way, where we replace y with y plus 4 and bring the 4 over. That gives you this, and then put in the 3x for y. And again, the equations end up being the same, so order here, in this case, does not matter. Replacing, on the part B here, replacing x with 2/3 x and y with negative 3y and x with x plus 2. Now what happened, I just want to see what happened over here. We did a stretch, that was a horizontal stretch, and then a movement at 90 degrees, it was a translation. So as long as these are at 90 degrees, order doesn't matter, as you can see. Let's see, you can see down here order does matter, but let's see why. This was a, again, a horizontal, just going to be a horizontal stretch. This is a reflection in the y-axis, so this is a reflection. Sorry, a reflection in the x-axis. So in x-axis. And then this is a movement to the left by 2. So translation left by 2. So what do we have? Horizontal stretch, reflection in x. Well, that would be a vertical thing to the horizontal movement, so that's okay. So this is vertical, things being flipped vertically, and then this is a translation 2 to the left. But this translation is horizontal, and so is this. So I'm thinking, yeah, that's probably why order matters. So they go around here and look at the equations of putting them in one order. Notice they do, as they've stated here, x changes to 2/3 x, y changes to negative 3y, and then finally translation 2 to the left. So in this equation, x here, this x, gets replaced with x plus 2. So right here, we change x to brackets x plus 2. Okay. Now doing it a different way, putting in this factor first, let's do these all backwards. Replacing x with x plus 2, replacing y with negative 3y, and finally we get that. We can bring the negative 3 to the other side to get this. And then we replace x with 2/3 x. So this x here gets replaced right here. What happens next is that they factor out the 2/3 out of both this and the 2, leaving this. So this changes actually to x plus 3. Now you can see that this equation compared to this equation is different. This actually would have been moved to the left by 2, this would be moved to the left by 3. Slight difference. So order does matter in this case. Okay, this graph here, parabola, y equals x squared plus 1, so that's this one here. Oops, choose my pen. X squared plus 1. The following transformations are applied in the order shown. Horizontal translation. Okay, that's right and left. Reflection in the x-axis. That's 90 degrees to each other. Then a vertical stretch. And then a vertical translation. Well, let's see what happens there. So, the first one is a horizontal translation 2 units left. So we end up going from here to here. That's the first transformation. Second one is reflection in the x-axis. So you go to this one here, this dotted line, number 2. And then 3, vertical stretch by the x-axis by a half. Okay, then anything at 1 goes to a half. Anything at 4 goes to 2, and so on. So you get this graph here with the dashed lines, followed by finally a vertical translation 3 units down. So this dashed line goes from here down to here. For each transformation, graph the image on the grid. Well, you can see it right here. And write the replacement for x or y and the current equation in the table. So I'm just going to scroll down here. So the translation, first one was a horizontal translation by 2, and it was to the left. So we get x changing to x plus 2. So replacing in the equation, which was originally, of course, x squared plus 1, x gets replaced with x plus 2. Next was a reflection in the x-axis. That means the y's become negative. So we'll change that to negative y, which we do. And then multiply both sides by negative 1. So we get this right here. Third, a vertical stretch by a factor of a half. Vertical stretch. We apply that to y. Y becomes 2y because it's a factor of 0.5, a half. So plugging 2y in where we see y as before, this equation, we can multiply or try to divide both sides by 2. So we get this. So we're now sitting here. And finally, a vertical translation 3 units down. A vertical translation down, y would change to y plus 3. So again, put y plus 3 here to get this, and bring it to the other side. So in bringing it to the other side, we are subtracting 3. So it'll be negative a half minus 3 we'll get. So that turns into negative 7 over 2. Write the equation that represents the final position of the graph and verify using a graphing calculator. So you can do that and check that. Make sure that you do get graph 4 here above. Okay, so let me just pause. Alright, so please do all the questions in this assignment for tomorrow, in the class tomorrow. Thanks.